Welcome, everybody. Started in just a minute here. 10 live. See you all is here. Cool. Ooh, that's gross. Welcome, welcome, welcome. All right. Let's give it another minute. Oh, by the way, here is the usual link to the attendance form. Please go fill it out once and only once when you have a chance. A couple people in my other class accidentally filled it out twice, so they got counted twice. So just do it once per class. Thank you, appreciate it. What else here? So I've definitely been looking at the material for Nandari and for Whitener, and you guys are going in very different directions currently, which might make things a little bit challenging here. I'm not sure how we're going to accommodate that exactly, but we might have to, I don't know. I'm not sure. We might do Tuesdays one class, Thursdays the other class. We might do, yeah, I'm not sure. So I've got a couple examples already kind of thought of today because both classes have talked about conditional probability a little bit. So I thought that would be worth going over for everyone because it is a concept that can be a little bit challenging to understand at first. But other than that, if you guys have questions, you should definitely be prepared to ask them after we go over these couple of examples I have thought up here. So again, here is the link to the attendance. Turn on my light, it's a little bit not as bright as I would like it to be in here. And again, if you want to bookmark that link to the attendance and just fill it out every time you come to class, that'd be great. I'm happy to post it in the chat every time, but if you want. So, conditional probability. Oh, let me do this so I can see my face. There we go. Conditional probability. The idea behind, for quiz 2. Oh, sure. Yeah, totally. Probably. So, exactly. So this notation, P of A, means the probability that that event occurs. So for real example, let's say, what have I got here? Let's say there are 8 balls in an urn, and 5 of them are red, and 3 of them are blue. And A is the event. We usually call things that happen events. A is the event that I draw, that I pick a red ball. And B is the event that I pick a blue ball. So then P of A is the probability that event A occurs. So if I'm just picking one ball, what's P of A? Well, there's 5 red, there's 8 total, so there's a 5 in 8 chance that I'm going to pick a red one. So the probability that event A occurs is 5 out of 8. This picture may be not so great for this particular example. Whereas the probability that B occurs is 3 out of 8. Wow, that's an 8, sure. So that's kind of how, that's the very basic beginning of that notation. We use a capital P parentheses surrounding the name of the event or the letter we designated the event to be. And then that's how we say, oh, we want to find the probability of this thing occurring. Let me, once again, here's the link to the attendance. Where is it? Sorry. There we go. So I could ask something like, so let's say I'm going to pick 2 balls. 2 balls without replacement. Meaning I pick one, I look at it, I see that it's some color, and then I pick another one. Sure, totally. In fact, so we'll go over a different question maybe, because again, not that I really care about going over the quiz or not specifically. I would like the quiz to be an opportunity for you guys to try and do it on your own, just because you totally get full credit no matter what you do. I'm happy to kind of address those questions as well, but I would like you to do it more with your own knowledge, just so that I can kind of give you feedback. But I'm happy to do something very similar to the quiz. So yes. So pick 2 balls without replacement. What's the probability of getting 2 reds? So the way I would write this using my notation here, and I'm sorry, I'm getting a little bit lazy here. What's the probability of getting 2 red balls? I want the probability of, how do I write that actually? Sorry. So the notation here can be somewhat terrible. I essentially want the probability of A. No, that's bad notation, James. Sorry. So notation gets funky when you're writing things. So what are the probability of 2 reds? My notation is not great for this particular problem. So I will say people get kind of lazy with this notation. I would probably just write it this way: probability of 2 reds. There's probably another way of writing it that's perfectly fine. I'm not seeing it right off the bat. Guess. No. Anyway, here's what I'm thinking. So the probability of getting 2 reds, well, what's the probability the first ball is red? Yeah, I guess. Sure. So it's probably the first ball is red. Times, sorry. And the probability, times the probability the second ball is red. So there's kind of this notion that I will hopefully try to make clear as we go on, is that when one thing and another thing both have to happen, we multiply their probabilities together. And if one thing or another thing need to happen, we add their probabilities together. And it's not always quite so cut and dry, but that's kind of the basic. So if I want the first ball to be red and the second ball to be red, I need to multiply the probability the first one's red times the probability the second one's red. The probability the first ball is red is 5/8. But now that I've removed 1 ball, there's 7 balls left. 4 of them are red. So the probability that the second ball I pick is also red is going to be 4/7. And so the probability of getting 2 red balls is 20/56, which would reduce to something. You can divide it 2 and get, I don't really care, right? It's not the most important part of this. 5/14. Sure. Another question I could ask, and this is kind of where I'm trying to get at, is what's the probability that the second ball is red given that the first ball is red. Okay, well, let's say the first ball was red. I picked out a red ball. How many red balls are left? 4. How many total balls are left? 7. So given that the first ball is red, we know the probability the second ball is red is 4 sevenths. Now I know this seems like I'm kind of cutting to the chase. I'm going to explain more. But that's what we know, right? We know that we've got red and blue pens. I should have done this, right? So here's our 5 red balls. Here's our 3 blue balls. And if I know already that the first ball I picked was a red ball, then given that information, I know that the probability that the second ball is red is exactly 4 sevenths because there are 4 red balls left out of 7 red balls, out of 7 balls total. Now, there is a way of calculating this. And this is the conditional probability formula. The way of calculating the probability that of one thing given another thing, which I'm going to write generally up here. The probability, let me erase these because these are not super helpful at the moment. The probability of A given B is the probability that A and B happen divided by the probability of B. So the way I kind of think about this formula is that if I'm trying to find the probability of A given B, the world I'm living in is the world of just B. And this kind of goes along with this Venn diagram that I had drawn over here for a second. So if we're thinking about this circle being A and this circle being B, where the probabilities are kind of like the areas. So the probability that B happens is this area divided by the total area. The probability that A happens is this area divided by the total area. The probability of A intersect B is where they overlap. That's A intersect B, or A and B. And I can feel my voice starting to not feel so high. I haven't been drinking enough tea. This is it. Okay. And then I'm not going to fill it in, but all this together would be A union B. Maybe I will. So all of this, right, all of that would be A union B, or A or B. This is A and B. So if I want to find the probability of A given B, well, the word given is really what's key there. If it's given that B has happened, I'm in the space where just B has already happened. And so I want to find the probability that A is happening given that B has already happened. I'll say, okay, well, it's the probability that A happens in the world of B, which is A and B, right? This little green speck here, the intersection, divided by the total probability, but in this case, my total probability is the probability that B is happening because that's my whole world if that's given information. So back to this example, the probability that the second ball is red given that the first ball is red is going to look like this. It's going to look like the probability that the second ball is red and the first ball is red divided by the probability that the first ball is red. Right? I want the probability that both of these things happening, that's your A intersect B, divided by the probability that this given thing has already happened. That's my B. Okay, well, we can calculate this. In fact, we've already calculated most of it. The probability that the first ball and the second ball are both red, we already figured out was 5/14. I'm worried my number's not going to work out. I'm worried I'm making a mistake. But let's check it out. The probability that the first ball was red was, well, if I'm just looking at all the balls, that's going to be 5 out of 8. It worked. All right, it does work. And so if we simplify this, 5/14 divided by 5/8 is 5/14 times 8/5. The 5s cancel. You get 8/14, which reduces to 4/7. So this is kind of the idea here, right? That you can divide these probabilities to find the conditional probability. Now there's a lot more to it than just this, but this is kind of the basic idea. That if you're trying to find the probability of one thing given another thing, it's the probability that they both happen divided by the probability that the given thing happens. Okay, let's look at another example. One that's maybe a little bit less, I don't know, this feels a little bit hand wavy. Let's look at something with some more, what's what I'm looking for? Some more definite numbers. Okay, so here are the 2008 presidential election result votes by gender. So I'll read this to you guys so you make sure you see it. In 2008, males voted, 29.4 million males voted for Obama, 28.8 million males voted for McCain, and 1.8 million males voted for other. 39.2 million females voted for Obama, 30.1 million females voted for McCain, and 0.7 million females voted for other. And so, a couple questions I want to answer. First question, what's the probability that a person picked at random, voted for McCain, and was female? So, if I give these little letters to make them easier, so I'm going to call this M. So males M, females F. Actually, so I did this in the notes, and I'm going to do this here too. I kind of want to use M in two different places, but I don't want to use the same letter. So I'm going to say that this is O, this is M, and this is other, let's call it T. That's dumb. And then for male and female, instead of using M and F, I'm going to use F for female and not F complement for male. And gosh, can you guys see that okay? It looks really tiny on my screen. But I have it, I think, not very big. So maybe I should make it bigger. Maybe I can see it then. Just want to make sure it looks, oh yeah, you can kind of see that all right. Okay. So I want to find the probability the person voted for McCain and was female. So that's, when I hear the word and, I think of intersection. So I want to find the probability that someone voted for McCain and was female. Okay. So I can find that box on my chart. There's those people right there. So the probability of being voting for McCain and being female is 30.1 million out of the total. Now we don't know what the total is. We should add these up real quick here. So if we add these up, this plus this plus this is 60 million. I already know what the numbers are because I wrote this out earlier. And this plus this plus this is 70 million. So this is the total. We can also do the totals here. This plus this, I didn't actually look at these before. This is 68.6 million. This is 58.9 million. And this is 2.5 million. For a grand total of 130 million in either direction. Right, yeah. These numbers are pretty close to what was actually true. I made them a little bit nicer so it would be easier with the numbers. No, it will not always be out of the total. So it depends on what question is being asked. So if the question is asked, what's the probability that someone has these qualities? Then yes, it's usually out of the total. But we'll see in the second question in just a minute that if you change the phrasing, you change the meaning. So in this case, it's going to be 30.1 million divided by 130 million, which I would probably just leave like that. But if you want to get a percentage or a number, 30.1 million divided by 130 million gives us 0.2315. So you can say the probability is 0.2315, or you can say it's 23.15%. Either way is fine. Usually we default to an answer like this as a decimal, not as a percentage. But your teacher might ask for it as a percentage. So, oh, also, one more time, here's the attendance. To contrast that, this second question says, what's the probability the person voted for McCain given that they were female? So this looks different than this. This is the probability that they voted for McCain given that they were female. Okay. So this is where we already are saying, well, the person is female. So before we write out the formula here, let's just think about it. How many females are there? Well, the female total is right over there. There's 70 females. It's not 70 million females. And 60 million males. So I know that in this case, my quote unquote total, right, the whole world that I am working in is limited to just the total number of females. Now, how many females voted for McCain? Well, I know where that is. That's still right here. So out of all the females, 70 million of them, 30.1 million of them voted for McCain. So the difference here is that it's still the same number of people that voted for McCain, but since we're already given that we just want to know how many, given that they're female, how many of them voted for McCain, we are dividing by not the total, but the number of females. In this case, we get about 30.1 divided by 70. It's 43%. Or 0.43, no, actually 0.43 exactly. It's not an approximation, it's an exact number. Okay. So this number is probably a little bit more telling as far as what matters, because he just asks what if you look at this first piece of information, knowing that 23% of females voted for McCain, well, it doesn't really mean a whole lot because it's not telling us specific to females, right? If I said how many people voted for McCain, so what's the probability that the person just voted for McCain? Well, that would be all the people that voted for McCain out of the total. Which would be 58.9 million divided by 130 million. Again, getting my calculator right here. Is about 0.45. So what I'm kind of seeing when I look at this is, all right, given that they were a female, the probability that they voted for McCain was 0.43 or 43%. Whereas generally, the probability that someone's a McCain voter without knowing their gender is 45%. So I would say that, female voters were a little bit less likely to vote for McCain than the general population. We could also have seen that, I'm running out of room here. We could also contrast that with the probability that someone voted for McCain given that they were male, which I'm writing as being not female. Right? F complement is the not being female category. So that would be, I forgot, I knew there was something out there. So I could kind of do it this way, but I want to write out the formula. So the way I'm actually thinking about this some of the time is it's the probability of being a McCain voter and a male divided by the probability of being a male. Now, usually when we do this, we try and do this. Oh, sorry, there's a question there. Why would you not divide by 58.9 million or 70 million for, sorry, this one over here? I think that's, no, the first one. This one here. Okay, so the reason this one here is because I wasn't given any prior knowledge. I was just being asked, what's the probability that someone is a McCain voter and a female? But I didn't say given anything, right? So in that case, I have to like. So let me answer your question by kind of saying how you would get what you wanted. So this one, probability of being a McCain voter, given that you're female, is the 30.1 divided by 70. And then if I wanted to get the other one, the 30.1 divided by 58.9, that would actually be kind of the reverse, which would be the probability of what's probably that someone is female, given that they're a McCain voter. Now, depending on your teacher, I feel like Whitener might be less cool with this because we're kind of envisioning this as being male or female being the explanatory variable or the independent variable, and the way they voted being the dependent, or I forget what the word is actually. So it might be kind of weird to say it this way, but we're going to say it anyway. So this would be the probability of being a female and a McCain voter divided by the probability of voting for McCain. Now, here's the way you actually calculate this, which I'm kind of skipping over. I'm just looking at the numbers and be like, oh, well, there's, I got a little dizzy there, sorry. There's 30.1 million people who are female and McCain voters divided by 58.9 million McCain voters total. But here's what we're actually doing. This probability is the 30.1 million out of 130 million. And this probability, the probability of being a McCain voter, is not 58.9 million, right? It's 58.9 million out of the total. $58.9 million divided by 130 million. So, is that from my video? Sorry. Yeah, I did. Okay, good. So, what always ends up happening here is these denominators in the fractions cancel out. Right? If you flip and multiply, you're going to get this over this times 130 million over 58.9, which is going to end up having 30 million, the 130 millions canceling and getting just 30.1 million over 58.9 million, which ends up being about 30.1 divided by 58.9, about 51%, or 0.511. I'm sorry, I erased this one. This was something to be really, really cognizant of, and this comes up a lot when we'll start talking about some examples with like diagnostic testing, like to test if someone has a disease, if they test positive or negative. The conditional probabilities in opposite directions are not the same, and often they are really, really different, actually. Sometimes they're not even close to the same. So the probability that someone is a McCain voter given that they're female is not the same as the probability that someone's female given that they're a McCain voter. They might be close, but they might be really, really wildly different. So something important to be kind of aware of. Oh, man. I'm talking too much. So, okay. So back over here for a second. So this calculation, I could do one of two ways. I could think of it just this way. I want to know what the probability of being a McCain voter is given that I'm male. Well, that's just going to be the number of male McCain voters divided by the number of males. And that's how we find the probability. It's the probability of the number of things you want divided by the total number of things it's supposed to be out of. In this case, it's out of being a male, since that is the given information. So here, we can calculate it this way and just say, all right, this is going to be, well, male McCain voters are right here, divided by the total number of males, which is 60 million. And again, not that the math here really matters that much, but we get exactly 0.48. But we could also have done it this way and say, well, if the probability of being a male and, a McCain voter and a male, doing it that way, it's the same, but it's a little different. This is going to be, well, the probability here, and you're going to, oh, actually, I'll say this in a bit, is going to be, well, to be probability of being a male and a McCain voter. Sorry, I got that backwards. A male and a McCain voter. That's going to be that divided by the total population. Divided by the probability of being a male, which is going to be the number of males out of the total population. I should say, this is not the actual population of people, right? This is the population of people that voted. Right? There aren't 130 million people in the US in 2008. There's more like 300 million. So, but look, these are just the same calculations, right? In this second calculation, these definitely cancel out, and you get 28.8 over 60, which is exactly that. So you can kind of think of these in two different ways. So hopefully, Shelby, that kind of answers your question about the quiz that I posted, because I think this example is fairly similar in idea to what the quiz has been asking about the smokers and non-smokers. Let's see. Oh man, yeah, my voice. I gotta talk less. It's hard not to talk. Okay. Let's look at another example, which I think is a pretty decent example. I kind of started doing one like this last time. So yeah. So let's say we roll 2 dice. A green die. Sorry, I should say 6-sided dice, and a red die. But you don't need these fun pictures, but I like fun pictures. And right, they have the pips on them, or what these little numbers are called. And you know, something like this. So there's a couple dice. And I want to ask some questions about the probability of what we can roll. And yes, you can kind of see this. Fun fact about 6-sided dice and most dice, the opposite sides should add up to 7, or whatever the number of sides is plus 1. And so if it's a regular set of dice, 1 should always be opposite 6, 2 should always be opposite 5, and 3 should always be opposite 4. So I want to know, what's the probability of rolling dice that sum to 9? Okay. So we have to find all the ways the dice can add to 9. Well, I can think of a few. Now I'm going to kind of do this wrong at first just to point out how we need to think about this. So the highest number on one die is 6. So we either have a 6 and a 3, or a 5 and a 4. Are there any other ways I could roll a 9? Well, the answer is it kind of depends on how you think about it. One way you could think about it is you say, no, these are definitely the only ways you can roll a 9. But you might say, well, depends on if you're which die you're talking about. Like you could say, I could have a red 6, the red die be 6, and the green die be 3, I could have the red die be 5 and the green die be 4, but I could also have the red die be 4 and the green die be 5, and the red die be 3 and the green die be 6. So while there's two different ways of getting a 9, there's actually 4 distinct ways of rolling a 9. Now, that's still not a probability. And there's something I've kind of failed to say about probabilities, which is really important. So whenever you're talking about probability, the probability of any event happening, and I know that Nindari is using like a capital E to represent an event, a probability should always be between 0 and 1, or between 0% and 100%. Right? You can't have something happen with a probability greater than 100%. That doesn't make any sense. Likewise, you can't have something happen with a negative probability. So these are things that are always true about probability. So between 0 and 1, between 0% and 100%. So I want to know what's the probability of the dice rolling to a 9. Well, again, the way I'm really going to calculate this is it's the number of ways of getting 9 divided by the total number of ways the dice can roll. Okay, how many different ways can the dice roll? How many different combinations are there when you roll 2 6-sided dice? Well, we can either make a list. In fact, we're going to make a list. Let's do the list. So these lists get a little bit tedious, but they are useful when we're first starting out. So we have the red die here. You pulled up the green pen. So the red die can roll a 1, a 2, a 3, a 4, a 5, or a 6. And the green die, a 1, a 2, a 3, a 4, a 5, or a 6. And then we can have all the combinations. So here we can have a 1 and a 1, a 1 and a 2, a 1 and a 3, 1 and a 4, 1 and a 5, 1 and a 6, and so on. Right, this does get a little bit tedious. So let me ask you, as I'm writing this out, I think it should be easier to see how many total possibilities are we going to have. Feel free to say it. Feel free to type it in the chat. Huh, it's a lot of writing. Okay. $36, exactly, yes. Now, instead of writing out every combination, I could have also thought about, well, there's 6 possibilities for the red die. There's 6 possibilities for the green die. And so since those things don't really depend on each other at all, there's 6 times 6 or 36 total possible outcomes. Now, some of them seem the same, right? These 2 outcomes right here, if the dice weren't colored differently than each other, they might feel like, oh, well, it's the same either way. They're technically not, but something to be aware of. So there's 2 ways you can roll a 3. There's 3 ways you could roll dice so that they add up to 4. A 1 and a 3, a 2 and a 2, or a 3 and a 1. Right here, the red die is 3 and the green die is 1. Here, the red die is 1 and the green die is 3. So how many ways are there of getting a 9? Well, the nice kind of thing about this table is that the diagonal lines this way all add up to the same thing. So, excuse me, where'd you go? There's my diagonal line where all the 9s are. So the probability of getting a 9 is 4 out of 36. 4 ways of getting a 9 out of 36 things total, which reduces to 1/9, which is totally what's the word I'm looking for? Coincidental that it happens to be 1 divided by 9. Right? If I said, what's the probability of getting a, so there are ways of making this easier to write. If I say like capital X is the sum of the dice, then I could write what's the probability that X is equal to 11. What's the probability that the dice add up to 11 when I roll them? Well, there's exactly 2 ways of getting an 11, a 5 and a 6 or a 6 and a 5. So that's going to be 2 out of 36, which reduces to 1 out of 18. I could also ask something like, what's the probability that X is greater than or equal to 8? So now I know all the ways I can get 8 or more. So I could write this out as the probability that X equals 8 plus the probability that X equals 9 plus the probability that X equals 10 plus the probability that X equals 11 plus the probability that X equals 12. And then add them all up. So X equals 8. There's 1, 2, 3, 4, 5 ways of being 8. So that's 5 out of 36 plus 4 ways of being 9 plus 3 ways of being 10. Sorry, I know it's getting small. Plus 2 ways of being 11 plus 1 way of being 12. So 5 plus 4 plus 3 plus 2 plus 1, that's going to give me 15 out of 36, or reducing out of 12. And then you can start asking some questions like, what's the probability that the total is 9, given that the red die is odd? Okay, so where's the pen to use here? So where's the red die odd? Well, here and here and here. So how many, what's the entirety of the space, or how many results are there where the red die is the one that is odd? How many are there in these 3 rows? Well, it looks like it's exactly half the time, right? If there are 36 total possibilities, half of them are going to be when the red die is odd, half of them are going to be when the red die is even. So one way to think about this would be to say, well, the red die is odd. There's 18 ways the red die can be odd. Now, how can I get X equal to 9 when the red die is odd? Well, let's see. There's one. Oh, that's not it. Sorry, not that one. There's one where the total is 9 and the red die is odd. And it looks like there's one as well. So I'm getting 2 out of 18. Just still 1/9. You also could have calculated this by doing the probability that X, equals 9, given that the red die is odd. You could have done it as the probability that X equals 9 and the red one is odd, divided by the probability that the red one is odd. And it's the same kind of thing, it's just a tiny bit different in the way we think about it. Here, the probability that X is 9 and red is odd, well, probably the sum is 9 and the red one is odd is there are exactly 2 ways out of 36 ways where the total is 9 and the red one is odd. But then there's exactly, divided by the probability the red one is odd, there's exactly 18 out of 36 ways. So it's the same thing, just slightly different math. So here's an interesting thing to know about this. The total being 9 and the red die being odd are what is known as independent events. And here's why. I'm going to erase this. So the events, and I'll write this generally. So A and B are independent events meaning that knowing one of them doesn't affect the probability of the other one if the probability of A given B is equal to the probability of A. Or the other way. Probability of B given A is equal to the probability of B. What this is saying is probability of A given that I know B is the same as the probability of A. So that knowing B doesn't actually change the probability of A. And that's definitely true in this last example, because we had the probability that that x equals 9 was 1/9, and the probability that x equal to 9, given that the red die was odd, is also 1/9. So those two events are considered independent, because knowing that the red die is odd doesn't affect the probability that the total of the dice adds up to 9. Let's see. There's something else I want to say about this. Let's do one more example. Let's find the probability that what do we got here? That the sum of the dice is less than or equal to 6, given that the green die, I was going to say the first die, the green is 3. I'll take it 4. Okay. So, I know I erased my table, so I'm just going to do this. So, how many ways can the total be less than or equal to 6 if the green die is 4? Well, it looks like there's like 2 ways, right? The red die can be 1, or the red die can be 2. There's no other choices. So there's going to be 2 ways out of what? It's a good question. So if we know the green die is 4, how many possibilities are there where the green die is 4? Well, I know I erased my picture, but if you remember, right, from the table, if here's green equal to 4, and there's exactly 6 possibilities with that green die being 4 and the red die being something else. So the probability that the total is less than 6, given that the green die is equal to 4, is 1/3. You could also do this the long way, right? You could say it's the probability that the total is less than or equal to 6 and the green die is equal to 4, divided by the probability that the green die is equal to 4. And the difference here is that this way, the probability on top is, well, it's the number of ways this can happen out of the total number of things that can happen. Same deal here. Probability the green equals 4 is the number of ways that can happen divided by the total number of ways. And then those always end up canceling. So it's the same. I want to contrast that with, I know we're out of time, but let me just say one last thing. I want to contrast that with what's the probability that the sum of the dice is less than 6? Well, there are a number of ways this can happen. You can either have x equal to 2, x equal to 3, all the way up to x equal to 6. So how many ways can you roll a 2? Well, there's one way, right? Snake eyes. How many ways can you roll a 3? There are 2 ways. How many ways can you roll a 4? There are 3 ways. Up until x equal to 7, they just keep increasing, right? There's 4 ways to roll a 5. There are 5 ways to roll a 6. And there are 6 ways to roll a 7, and then you go back down. There's 5 ways to roll an 8, there's 4 ways to roll a 9, et cetera, et cetera, et cetera. So then if we add this up, we get 15 out of 36, which reduces to 5 out of 12. And the point I want to make here is that these are not the same, which means these events are not independent. So knowing that the green die is equal to 4 affects the probability that the total is less than or equal to 6, because we get different numbers based on with this conditional probability versus this unconditional probability over here. So that's all I really have to say. Let me know what you want to see on Thursday. I know the Whitener people and the Nandari people have kind of different stuff going on, but if you let me know ahead of time, I can better try to give you guys what you want. And maybe we'll try doing like the breakout rooms and have people in Nandari's class in one room, people in Whitener's class in the other. We might not, I don't know. So I'll see you guys on Thursday, and let me know if you have questions. Let me know if there are things you want to be seeing that I didn't get to today. And yeah, take care. I'll see. Ow, son of a gun! I cut my finger and I just opened the wound. All right, I'll see you guys Thursday. Sorry. Oh, and make sure you fill out the attendance.